Welcome to this week's lecture. We are in week 7 of Object-Oriented Programming 1, and today we talk about smart pointer and casts. So, as you can see, I'm still alone. Alex is still a bit sick, and I think next time, so in 2 weeks, because next time is holiday, in 2 weeks he will be here and holding the lecture. So we are already, at the 8th lecture, I think, or a 7th lecture, 8 altogether. Today we talk about smart pointers, and as I said, in 2 weeks, then we talk about templates and selected topics. As I said last time, my opinion, most of the object-oriented topics are already shown in the previous lectures, so in the general object-oriented paradigms. This week, so the smart pointer and the casts, and also next week where we talk about templates and also some selected topics, is more C++ specific. So maybe this is then the difference between a good C++ programmer and an expert in C++ to work with smart pointers and with templates. So the general part is over, in my opinion, and now we are coming to the more deeper C++ specific topics. Okay, as always, what's the question already? No. As always, let's start with a short quiz from last time about operators. I think you have seen a lot of operator overloading in the practicals, and I prepared a short quiz for you. I will give you about a minute, so take your time. All right, I know it's not that easy. Few seconds left, then we start. Maybe we can reach the 40 participants. Yes, great. So, to be honest, I built in some kind of a trap here, but most of you, or not most of you, but half of you spotted it. Great, well done. The result is just night. Why is this the case? So we have a character here, or two characters, first and second, NI and GHT, and we use this plus operator, which is here implemented, and this just returns this name plus the right-hand side name, and it returns a string. It does not return a character in this case, it returns a string. So the outcome of this here is a string, and we just print out a string. So this operator here is never called. It's some kind of a trap, yeah. But in this case, it's just printed a string, and this operator, this overloaded operator, is never called here. Any questions to this? Yes? This here? So this is first in this case. So this name in this case is NI, because it's the left side. Other questions? Yes?
So you call this operator for the CL first with the smaller sign, and why doesn't it call the definition of the operator?
Sorry, once again?
So you're using this CL operator with the smaller sign?
Here.
Yes.
Yeah?
And we have a function which really defines it.
Yeah?
So why isn't this function being called?
Because this function, you mean this function here, right? This function takes a character, a reference of a character. But the outcome, so the right side of this operator here, is a string. This is a string here. Because if we add two characters, the output, so the result is a string. So in this case, it checks, okay, the left side is this O stream, and the right side of this operator here is just a string. So I do not use this operator here. I use the default operator to print out strings. So this one is never called. There is no error, yes. It's valid because I could use it somewhere else. But in this case, this operator here is not used, yeah.
So then when we have this, when we define an operator, still the both types of operator exist, the redefined one and the original one?
So you mean when we override here the string operator? So this would also work, yeah. You could also override the string operator to make like a custom string output when you want to print out a string, and let's say before each string you want to have, I don't know, a line number or whatever. This would also work. So you can also override let's say, for example, the output for strings. Was this the question?
It was rather when we overrode this operator with the smaller sign, and now because it's not being called in the last line with the CL, so basically this means that now we have two such operators with smaller sign. We have the original one from the C++ language, and we have this one already defined.
So there are in general, so the question is, do we have now more than one overloaded operator? In general, in the C++ standard library, there's a bunch of operators which are overloaded already. So each string operation, when you do a concatenation of strings or whatever, there is already an operator overloading implementation in the library. So you can use it. But in this case, we have one here, but here we use the overloading, so this the operator overloading from the library, which is already implemented by somebody else. Okay, any other questions? Then let's move on. And before we talk about smart pointers, let's talk about casts. And I think Michi already spoiled it a bit, what casts are. You know casts also maybe from C already. And the C way of casting is you write here this new type before the expression. So for example, we have a float. And then I say, okay, I want to convert this to an integer. So I write here inside this parenthesis the data type and then the variable name, and I get back an integer. This works great in C++, there are 4 types of casts now. And we will discuss all of them: the static cast, the reinterpret cast, the const cast, and the dynamic cast. Let's go ahead with the static cast. So each cast has its own use case, and let's start with the static cast. The static cast is most likely the one with which is most commonly used, which is also comparable to the one you know from C. But the only difference here is that the compiler checks that you want to do a conversion from one type to another, and already the compiler checks if it's possible to do this conversion. In C, it is not possible. This is only checked in runtime if your cast works, and if not, there is an error then at runtime. With this static cast, you have an error at compile time, which may be better for you because you know earlier that there's a problem. So here is a short example. I know it's, again, a little bit more to write. That's C++. We have here an integer number, and we want to convert this to a double. So we write static cast, then here the double, the new data type, and the variable we want to cast, and we get back, in this case, a double. We could also use it, for example, for pointers. So we take here the address of this I integer and convert this to a void pointer. We get back a void pointer, and we can also convert this then, for example, to an integer pointer, and this also works. The static cast only works if there is there is a conversion known by the compiler. So, for example, if you have here an integer pointer or an address, you cannot convert it to just, I don't know, a float. The compiler will say this is not possible, you should not do this, I will not compile your program. So, especially in the beginning, this kind of castings or castings is something else. This kind of casts is very helpful when you don't know exactly which data type is a good idea to cast and which not. The other one, the next one, is the dynamic cast. And dynamic cast is used when you use inheritance. So this performs like a downcasting, so you can convert pointers or references from the base class down to the derived class. And again, we have here a check for validity. If we have a requirement that if you use this dynamic cast, at least one virtual method has to be present in the base class. And again, you have at runtime here a check. And if the conversion is not possible, it does not just crash. It returns a null pointer when the pointer conversion does not work, and it throws a bad cast exception for a reference conversion that did not work. So a short example, we have here our well-known animal with a lion derived from the animal, and when we say something like this, so we create first a lion and write it into an animal, and then we say, okay, I want it to be a lion again, then I can make a dynamic cast, so I cast it back to a lion, and I check here if the cast worked. The third cast is one you should avoid, to be honest, but sometimes it's necessary. It's the so-called const cast, and it removes the constancy or the constness of a variable to make objects modifiable. So, for example, we have here a function getLion, which returns a const lion pointer, meaning that you cannot modify this lion. Sometimes, and only sometimes, you might need to modify this. So in this case, if you write it like this, you will get an error because it says, okay, this returns a const line pointer. You just take a line pointer. This will not work. There is no conversion about that. What you can do is you can write a const cast line pointer. So you cast this now to a normal line pointer, not a const line pointer, and then you can work with this line and modify this line in this case, or this variable here. As I said, please don't use it too often because it basically destroys the const mechanism completely. So in my experience, I only used it once or twice when I have a library and this library returned me a const object, and for debugging purpose, I just wanted to have a look what's inside and maybe modify this object a bit just to print it out, and then you can use this const cast. Otherwise, I would not recommend to do it that often. And the last cast is the so-called reinterpret cast. And this is the cast which do not check that much. This is, the most similar one to the C cast, let's call it like this. So there are no checks on type safety, and you should also avoid it if possible because the other might fit better in this case. But what you can do is, for example, when you have a lion and you can, this is a lion pointer, and you can call reinterpret cast, for example, cast it to an integer pointer for whatever reason you want to do that. And you could also reinterpret cast it to long, which works because a pointer is just an address. An address has 8 bytes, and a long also has 8 bytes. So you're just storing the address in a long. This would work in general, but I don't know a use case for this for our purpose. Maybe in the next semester for operating systems, there would be a use case for that. Okay, any questions? I know they are, so I've gone through that very, very fast. What you should remember, there are 4 casts. They have different purpose, but I will come to a summary in the next slide, but any questions to these 4 casts now? Yes? No. So also the question is, could we use this reinterpret cast to convert a string to an integer? No, this would not work. You have to use the methods for that. So string to int, for example, from the standard library, stoy is it called, I think. This would not work because even the reinterpret cast would say that this is not allowed. Any other questions? Then let's make a short quiz again. What do you think, which scenario is the most appropriate for using a dynamic cast? All right. Again, we have reached the 40. So, yes, most of you spotted it. Great. Converting a base class pointer to a derived class pointer with runtime type checking. This is the most appropriate use case. Of course, the second one, convert a derived class pointer to a base class pointer, would also work with dynamic cast, but the first one is the one which is often used for dynamic casts. Okay, so the question might come now, why should I use C++ casts over C casts? They are more to write, so I have to know which one should I take. Why not take just the C type or the C casts? And there are a few differences, of course. So, as I said, the C++ casts are checked by the compiler. The C casts are not checked by the compiler. The C++ casts then, of course, fail at compile time if there is an error. The C casts fail at runtime. And this is always a bit, a problem, because it might also then fail when you have the program already delivered to your user or whatever. C++ casts have different use cases, so depending on which cast you take. And for C cast, there is only one, which makes it for C++ clearer which one should I use. And for C, it's just, you don't know, or you just take one for every case, and that's why it cannot be checked that explicitly. And what's maybe also a very important thing afterwards, if you have a huge code base, C++ casts are easier to find. C casts are typically hard to find. In C++ casts, you just search for static cast, dynamic cast, and then you know where you have your castings or your casts. I always say castings, I don't know why. So in general, I would say C++ casts are better, especially for beginners. Beginners benefit from the advantages of C++ casts, especially because they are checked by the compiler. But my personal opinion, if you know what you are doing, you can also use the C casts, but you have to know what you are doing. And we defined for the practicals, please use the C++ casts, but I know later on in, let's say, system level programming or operating system, when you are more familiar and know C++ even better, then you might end up again with the C casts. I also have done it, so I only want to show it to you. There are C++ casts which could help you, especially when you start with C++. All right, any questions to casts in general? Yes?
Admittedly, it's not completely related to this topic, but is C++ actually a subset of the C language, a real subset of C++?
Yes, so in general, the question is C like a subset of C++? You can write every C code inside C++, yeah? This works. Not the other way around, but you can write every C code, and you can also use all the C libraries in C++. So it works. But then you're not writing real C++, you're writing C in a C++ file. But it would work, yeah. All right. Then let's go on to the, on my opinion, more interesting topic. And it's about smart pointers. And these smart pointers might help you a lot, especially at your assignments. But before, I want to know from you, what do you not like about pointers, or maybe the heap in general? What do you hate? Yes?
Always have to think about freeing it.
Yes, that's the hardest thing to do. Always, when I use the heap or when I use pointers in general, I have to free it afterwards. Any other things that get you a headache about pointers? Yes? The types, yeah, you need to think of the types of the pointers, yeah. And my opinion also sometimes, I don't know, I have to dereference a pointer. Do I have the pointer now, especially when I have a pointer? Is it now twice to dereference or not? So this is very hard. And the cool thing about smart pointers is that they help you a lot. So in C, or not in C, but with pointers, we have something like this. We have a superhero class. We will use this superhero class for the rest of the lecture now. It's always the same. It has a name, a constructor with a string, and it just prints out the name and then create it. It has an attack method, print out the name and attacks, and then a destructor with the name and destroyed. And we have here the superhero, which is created on the heap, and obviously, hopefully most of you have spotted it. This creates a Valgrind error because Batman is created, here is printed, but it's never destroyed. So we have a memory leak here. Another thing at pointers, which in this case maybe is too obvious, but sometimes it's harder to find when we have here an object and we delete it, and then we call, let's say, a method of it. This memory is already freed, so this is called a dangling pointer, and this is also a problem because we access here memory which we do not have anymore. So pointers in general can cause memory leaks, create wild pointers or dangling pointers, and we have to free and delete all this memory where the pointer points to. So in general, I think it can cause a lot of headache. Smart pointers helps us a lot. So smart pointers are like wrapper around pointers. So it's like an own class where the pointer is one member of this smart pointer class. And it is used for a heap allocation. It acts like a raw pointer. So when I say raw pointer, I mean like the normal pointer. This is the raw pointer, and the smart pointer has an attribute of which is the raw pointer then. But the smart pointer helps us because it destroys itself. So you do not have to deal with where do you want to delete it or when do you want to delete it. Using smart pointers, you will not have any memory leaks left. And I think that's promising for your assignments because that's always a thing everybody takes a lot of time looking for memory leaks. There are 3 types of smart pointers, and we will discuss them now. We have a unique pointer, a shared pointer, and a weak pointer. For all of them, you just need to include this memory library, and then you can start with it. Okay, let's start with the unique pointer. That's the easiest one. It's the most similar one to our pointer we know. So the unique pointer points exactly to one object. And as soon as it goes out of scope, it will automatically destroy itself or destroy the object it points to. The unique pointer cannot be copied or assigned to other pointers. That's why they are called unique, and it's also called exclusive ownership. So you have here a superhero object, and you have a pointer which points to this superhero. And when you want to copy the pointer to this same object, this will not work. So C++ will say it's not possible to copy a unique pointer. It's only possible to have one pointer pointing to this object. So this is a easy use case. Again, we have here our superhero class. We include the memory library here. And we just create here a unique pointer for our superhero. I know it's, again, a lot to write. What you typically can do is write auto here, because it's much easier then. But just for you to get an understanding how this works, I've written it here always. So we have here in the standard library a unique pointer, and from type superhero, so this is just the data type, the variable name is this S1, and we create this unique pointer by calling make unique with a data type, and then we call the constructor here. So the constructor of superhero takes a string, so we hand over the string there. And this will create us, at first place, our superhero object, and additionally a smart pointer to this object. So we have, when we go back, we have both here now. We have created the object and a pointer to this object. Like you also get when you create something on the heap, you get the object and a pointer to this object. This is pretty similar, but you get a little bit more. You get not only the pointer to the object, but also the class that covers that pointer to the object. So this unique pointer class contains a little bit more than just a pointer, but we will come to that. So as you also can see in the output, this make unique here creates the object, so it calls the constructor. That's why Batman created here is printed. And then when it goes out of scope, and in scope means the lifetime of the variable S1 here is over, which is just when the program ends. And then it automatically calls the destructor of the, in this case, superhero class, and Batman destroyed is printed. That's the body of the destructor here. So when we compare this with, also with Valgrind, you can see that, of course, both is printed and we do not have any memory leaks here. So everything is freed correctly. When we compare this to our raw pointer, we have now just a create new superhero with Batman, and this one will be stored into a normal superhero pointer. When we do it, when we check it with Valgrind, just Batman created, so just the constructor is executed. The destructor here is never executed because it's never deleted, and we have memory leaks here. So this is the huge advantage when we go back here, where we created the smart pointer. When we go out of scope, it's just somewhere here. When this object is destroyed, automatically it calls the destructor, and you do not have to free something. That's a pretty cool thing, because you don't have to think about where do I need to delete this pointer or this pointer to the heap. Yes?
I have two questions. The first one is, now that we are doing these pointers, does it always make sense to use the smart pointers instead of all of the regular pointers?
Yes. So the question is, does it make sense that I use only smart pointer instead of regular pointers, right?
Is there any reason why in our C++ programs we should still have regular pointers? Or?
So if you have a pointer on the stack or pointer to the stack, it doesn't make sense to have a smart pointer. They are only helpful when you have heap memory. Yeah. So if you have a pointer on your stack, just use a pointer there, because you don't have the problem that the object is not destroyed. It gets destroyed anyway when the scope of the variable is over. But when you have, as soon as you work with the heap, in my opinion, there's no advantage. Maybe one advantage using raw pointers instead of smart pointers is smart pointers have a little bit more overhead, so they need more memory, of course, because they have to store a few more things under the hood inside this class. So if you're working with very, very reduced memory, but we are talking here about less than a few kilobytes, then it might be a good idea to use raw pointers, but in 99% of the cases, you can work with smart pointers, especially here in OOP1. Any other questions? Yes? We will come to that. We'll come to that, yeah? Any other questions now more to how we declare it in general? Okay, so copying in general is not that easy, or it's, completely not allowed. So when we create here a unique pointer, again, we say make unique. And let's say we have here a method called attack, which takes a unique pointer. First thing I want to do is I try to assign this S1, this superhero, this unique pointer to a superhero pointer. This gives me an error. This does not work at all because this is not really a pointer to the object, to the superhero. This is a pointer to the unique pointer class, which contains a pointer to the superhero. But also something like this is not possible. So you cannot create a unique pointer and hand over another pointer, because copying this unique pointer is not allowed. We will come to another concept, the shared pointer, where it is allowed. But sometimes, for some use cases, it's better that we are not allowed to copy pointers or copy pointers to the same object. And also, this line here is not allowed. This also gives us an error, because when we call this function, this object here is copied. It's just by value. So this will also not work because we implicitly create a copy of the object, and this is not allowed here. By the way, when you use smart pointers, you can access them again with this arrow. We will also see how you can get the true pointer, the raw pointer out of this smart pointer, but you can access it with this arrow to get then the methods inside the class. Any ideas how they achieved that it's not possible to assign or to copy this smart pointers? Yes?
Because the unique pointer is just a container for another pointer. In this class, they deleted the operator overloading for the equals.
Great. Yeah. So they basically just deleted the assignment operator, the copy constructor. So you cannot create a copy of this S1 variable. It's just not possible. And as soon as you create or write a line like this again, another object is created. So you cannot have another pointer or a second pointer to the same object here. It's just not possible because they deleted the copy constructor and the assignment operator. Yes? So the question is, can we copy unique pointers to what then?
Can we redefine them unique pointers in the standard library, like we did in the previous lectures?
Yeah.
To allow ourselves to copy unique pointers into other unique pointers.
So we cannot modify the standard library in general. But in general, unique pointers are not copyable, so you cannot copy them.
And what do you mean? So with the exceptions, for example,
So so in the standard library, we just override the methods from the standard library. So we do not really change the methods in the standard library when we use operator overloading. We're just overwriting them, which means there is another implementation of the same method, but we have to, or we want to define it. So the question here is now from you that is it possible to override this copy constructor of the unique pointer? Yeah, so what you could do is you can create your own unique pointer or smart pointer class in general, but it doesn't really make sense because the shared pointer fulfills all the criteria maybe you want to have, that you can copy and assign these pointers. So these unique pointers are designed that they are not copyable, and sometimes you want to use it like this. In most of the times, I know you will use the shared pointers where you can create copies, but we will come to that. Okay, yeah, as I said, in the unique pointer class, the copy constructor and the assignment operator are deleted, so this will not work here. But you can, of course, also change it a bit that it would work to copy like the unique pointer, but not really the pointer. One thing you could do is you can call the get method of this unique pointer class, and this get method returns you the raw pointer. So when you call s1.get, you can then get a pointer to the object. This is not a second unique pointer. This is just a pointer to the object, so a superhero pointer in this case. You can also write it like this and say, okay, I create a unique pointer with the pointer here from S1. Or what also would work, I call this call attack and take a superhero pointer and just hand over the pointer. So I don't hand over the unique pointer, so the smart pointer class object, but only this superhero pointer. But this has some problems. As soon as this S1 pointer here gets out of scope, which is here, the raw pointers are invalid. This case, it's not a big deal because it lives until all the pointers are used. But let's modify it a bit and say, okay, this should not be like this. I'm sorry. So this is only a declaration. Just think of that this isn't here. This one. So, okay. This is just a declaration of superhero pointer, and we have here an if, for whatever reason, we create inside a unique pointer, make unique. This creates me the unique pointer and the object. And then I say, okay, give me the pointer, so the raw pointer, and write it into this S2 variable here. And then we go out of scope of this unique pointer here. So as soon as we reach this line of code here, the unique pointer is destroyed and the object is destroyed. And then we want to use this pointer again, but the object is already destroyed. So this, in this case, when we hand it over and try to use the method attack, will not work again because the object is already destroyed. And this is a very important thing because you have to know how long does my pointer live here. So it gets destroyed at the end of this if here, and afterwards I cannot use it anymore. Yes?
Is this also vice versa? So if I take the unique pointer, give it to a raw pointer and I see the raw pointer, is the unique pointer losing its focus?
No. So the unique pointer is the unique pointer does not know that you call here a get and store the pointer somewhere else. It just thinks that this unique pointer here is the only pointer to the object, and when it goes out of scope, it thinks that there are no more pointers and just destroy the object. It doesn't know that we have copied the raw pointer, and the other way around is also not possible because the unique pointer have no information how many other pointers are pointing to this object. It just knows that it should be the only smart pointer pointing to this object. All right. So yes, as I said, the scope ends here and the object here is already deleted. Another solution is using the move method. So basically the same code. We create here our superhero and we call here our call attack method, which takes a unique pointer. And this will work now because we are moving the ownership of a unique pointer to another unique pointer. So this one moves the ownership of S1. So the ownership means you can think of it like the right to be able to point to the object. This is the ownership. And the S1 has here the right to point to the object, and we move it to the hero here. So here now the hero has the right to point to the object, but we cannot use S1 here anymore because it loses the right to point to this object. So basically when we use move, we have a pointer 1 pointing to an object. Then we call move, we create a second pointer, and as soon as the second pointer points to the object, the first pointer points to null then. This ensures again that there is only one pointer, so one unique pointer points to the object. All right, a short quiz again about unique pointers. So again, we have our superhero class. We have a method called create superhero, which creates a unique pointer, returns the s1.get. The question is, what is the output? So it's great that you discuss about it, but I think we can go on now. Again, I implemented here a short kind of trap. So there are many possible outcomes for this. The most likely is a runtime error. So the first thing is, yes, it does compile, because the compiler says it works. You are always allowed to return a pointer. You will get a warning, yes, because the compiler says you are returning a pointer created inside of the function. But it works in general. But it could also be the other way around, that it's printed or it's a runtime error. Why is this the case? So in general, what's the problem? The scope of S1 ends here, so this unique pointer is destroyed. You are returning here a pointer to an object which is already destroyed. So you get here back an object or a pointer to an object which is destroyed, and then you call the attack method. And this is then undefined behavior. It might be that it works, because it might be that the strings are left there and the object is still in the memory and no other process or whatever has overwritten this memory section. So it might be that you will, or that it prints correctly. Can be, cannot be, I don't know. Sometimes it works, sometimes it works not. Sometimes you get a segmentation fault, sometimes you get an infinite loop. It depends, but it will compile and it will result in a problem at all. Yes?
But will we always be Batman destroyed after read the sequence?
So yes, you will of course get the Batman created, yeah, and you will also get the Batman destroyed. That's why I marked them as valid, because it might be that Batman created, Batman attacks, Batman destroyed is printed. It could also be that in this way around, so Batman created, Batman destroyed, Batman attacks is printed. Depends a bit. Yes?
Wouldn't he always be destroyed as the second thing? So how can the third option be possible? Because isn't he always destroyed after being created?
It can be, because sometimes this output prints are buffered and they are not directly printed out. It is not very likely, but it can be that they are buffered. That's why sometimes they can change a bit, but this is a very, very unusual case here, yeah. So, but it is just undefined behavior, yes? Not really. I tried it with Clang++, and for 10 times I get 7 times a segmentation fault, 3 times or 2 times an infinite loop, and once it printed correctly. I don't know exactly what's going on there. It's just, it depends on if there is still this object and we access this object, which we do not have anymore, but sometimes it works, yeah. Yes? The question is, would it be possible to fix this by allocating memory on the heap? The problem is, you could do it without smart pointers here, yes, and just allocating here the heap, and then it would work perfectly, yeah? But then you have the disadvantage that you have to call delete here afterwards. So this is the disadvantage. Thank you. This is the disadvantage of smart pointers, because you have to think about how long is the scope. So how long does this variable live? When you just create here something on the heap by a new Superman or new superhero, then you return it. This would perfectly work, of course. Yes.
So basically, if we would like to use the pointer and the object then outside of this method, for example, in some other function or in the main, then we would better use the raw pointers and not the smart pointers.
Not really. So the question is, should we then use the raw pointers? No, because we are only discussing about unique pointers now. We will come to shared pointers and weak pointers. They are for use cases like this. Yes?
Just another question on that. So the unique pointers mainly used for the main.
No, that was the question already now. It's the unique pointers are not only for the main. It depends, yes, sometimes, but I will come to that. Sometimes or most of the time unique pointers are useful when you know that you need this pointer just inside a function with subfunctions, but not going back to a function, returning to a function. Yes, this then is a problem of a unique pointer. You could move it back with the move function. All right, but I think we should continue now to the shared pointers, because the shared pointers are the thing that doing things better when you need more than one pointer to the object. Yes? Yes, you can also pass pointers per reference, yes. Shared pointers can be copied, so this is the difference to unique pointers. Shared pointers, as the name suggests, can be shared. So you have a pointer, you can copy the pointer, and then you have another pointer. They're pointing to the same object. And again, the object will be destroyed automatically as soon as all pointers are out of scope. So it can be that one pointer goes out of scope, can be that another pointer goes out of scope, but it will only be destroyed when all the pointers go out of scope. Then the shared pointer thinks that you don't need this object anymore because you lost all the pointers, and then it destroys the object. So here, example, again, our superhero class with the familiar constructor method here and destructor. And the only difference is that we take here a shared pointer now, and we call make shared. And then we can call the attack method, and this works the same as before. So in this case, there is no difference to the unique pointer, but of course there are differences. Namely, when we copy this pointer. So before, all of this copy thing here was not work. Now it works that we create here a pointer. We assign this pointer to another pointer, so assignment works. We copy this pointer and create another pointer. So we now have 3 pointers pointing to the same object. And we can also call functions because this also creates a copy, but we have now 4 copies then. One is here and the other 3 are here. So this works perfectly, and I think this is the use case, or the let's say shared pointers are most used pointers or smart pointers, because this is in most cases the thing that you want to have more than one pointer pointing to the same object. So in this case, as I said, the pointers are copied and the object is the same. So we only create one object here in this line, and the rest is just creating new pointers. Of course, you can write here auto, which makes it much less to write. And this is also the advantage as we had before. Now this would work when we have this create superhero function. We create here a shared pointer. We are returning this shared pointer. Yes, this shared pointer, this S1 shared pointer goes out of scope. So this pointer is not valid anymore. But when we return it, it will create a copy of the pointer, so still one pointer is left pointing to the object, and then we can use this smart pointer here and call attack. This works perfectly. So it does not create or destroy the Batman object when the function here ends. Okay, so how do they work? So this shared pointer is an interesting concept. How do they know how many pointers are currently pointing to this object? And as I said, they are just a class. So the shared pointers is a class having one member, namely the raw pointer pointing to the object. And they have a so-called control block, which is just metadata, so data about the data. And in this control block, they have a so-called ref counter or reference counter, which just counts how many pointers were created that pointing to this object. So whenever a pointer gets copied, this reference counter is incremented, and all the shared pointers now know that there are altogether in my program, let's say, 3 pointers that points to this object. Of course, this only works if you copy the shared pointer object and not the raw pointer. If you copy the raw pointer, the shared pointer class cannot be notified, and this does not work. So when you work with smart pointers, I would highly recommend that you also only copy the smart pointers. Then always this reference count is incremented, and then you know how many pointers are currently in your project. And you can use this use count method of each shared pointer to see how many number of pointers pointing to this object currently. So this is again an example for our superhero class, and we want to go through this now line by line. So we are currently here in our program. After executing this line of code, what will be the output here? Any ideas? So we're declaring a shared pointer object of the superhero, call it S1. Does this produce an output? No, does not, exactly. Does not produce an output because it's just a variable declaration. It does not create the object. So next line, S1 use count. How many pointers are currently pointing to an object? It's 0, yes. So then we have 0 because we haven't even created an object now. Okay, after the next line, after executing this line, would be the output. Or is there an output? Yeah, we are assuming it's always the same. Then it's again our Batman created is printed. Okay. Then next line. What will be the output now? 1. Yeah. Next line. We copying this pointer. Is there an output now from the next line, from this line here? No, there's no output. It's just copying the pointer, but not creating a new object. Okay, next line. What's the output here? 2 and 2. Yes, correct. So we call this use count from the S1, and the S1 knows that there are currently two smart pointers or 2 shared pointers pointing to the same object, and also the S2 knows that there are 2 currently. Okay, anything left which will be printed after the return? Yes? Yes, exactly. So Batman destroyed is then printed because the object is destroyed. It's only printed once, of course, because we only have one object. We have two shared pointers, but both shared pointers go out of scope here. And that's the reason then why the destructor is called. Okay, any questions to shared pointers? Then let's go on to weak pointers. And they are, as the name also suggests, weak shared pointers. So they are similar to shared pointers, but they do not have this reference count. So they do not increment when this is created. So when we copy a shared pointer and store it as a weak pointer, this does not increment the reference count then. So you can use weak pointers, but you have to be, again, careful because it might be that the object is already destroyed. It is kind of like the raw pointer you're using when you use the weak pointer, but you have some advantages. But let's see how this works in general. You have here again a shared pointer. You will always call make shared. There is no make weak because weak pointers are designed to be a weak shared pointer. So it's only possible to combine a weak pointer with a shared pointer. And you cannot create a weak pointer in this case. You always have to create a shared pointer and then can create a weak pointer out of it. So you create here a shared pointer. Then you assign here or create a copy of the pointer, but store it in a weak pointer. And what will be the outcome here when we use or when we print out how many pointers, smart pointers there are currently pointing? Yes? 1. So it's again Batman created, 1, Batman destroyed, because the weak pointer does not increment the ref counter. Okay, the weak pointer has two advantages. It has a method called expired, which returns true if the object it points to is already destroyed, which might helpful, and otherwise it returns false. So you can call, okay, if S2 is already expired, then do something, or if it's not expired, do something else. And it also has a so-called lock method, and this is pretty cool because you now get ownership of the object, so it changes a weak pointer to a shared pointer. Sometimes in a situation you think, okay, I do not need to have a weak pointer, but in a certain constellation of if-else, then I want to create a shared pointer out of a weak pointer. You can call this lock method, and this then creates a shared pointer out of it, and you increment the ref counter of this object. The question might arise, why should I use a weak pointer when I can have a shared pointer? In general, sometimes you do not need to have a shared pointer because you know you will only, let's say, observing an object, you will not change it, and it's only in the scope of a function, then you can use a weak pointer. But in general, especially when you are new to shared pointers, I would recommend to stay at the shared pointers because you can deal with the overhead it produces. It's not a big deal. Okay, I think it's the last quiz for today. I think we are already, a few minutes left, but this is the last one. What is the output here? But I think we can also do it like this. I think we have 5 minutes left, so I can use it for the slides. What do you think is the outcome here? Any ideas? It's not that easy, to be honest. So this make shared will print what? Batman created, yeah, that's easy. Yeah? What will this as one use count will print? Okay, I've heard 1. Any other ideas? 0, yes, it's printing 0. And then is the question, when is this Batman, this superhero, destroyed? Does it happen before the use count or afterwards? And it is afterwards. It is before. So the Batman is destroyed before the number here. And the thing is that this one, when we store it in a weak pointer, it does not increment the ref count. So the ref count stays 0, and as soon as a shared pointer sees that the ref count is 0, it automatically destroys the object. So it creates the object and destroys the object immediately, and that's why there is no object anymore, and it is destroyed, and the ref counter is set to 0. All right, any questions to weak pointers? Yes? Yeah, sure. You can still run out of memory. This shared pointers or this make shared and this make unique here internally calls new. So if you run out of memory, you will get a bad alloc exception back, or not back. You will throw a bad alloc exception, and you have to catch it. Yes. All right, so to sum it up, we had three types of smart pointer. We had the unique pointer, the shared pointer, and the weak pointer. The unique pointer is where we have a single ownership, so just one pointer pointing to the object. The shared pointer has a shared ownership, so you have many of them. And the weak pointer has some kind of no ownership because it can point to an object, but it does not count as a pointer to this object. The unique pointer, as I said, cannot share the ownership. The shared pointer uses a ref count to track how many pointers are referring to this object. The weak pointer does not affect the ownership and the ref counter. And the use case for unique pointer is most of the time if you have non-shared objects. So when you know you will only have one pointer to this object. Maybe you use this object or you create this object and destroy this object after the function is over. Then you can use a unique pointer. In most of the cases, you will use a shared pointer, my opinion, because you can use it wherever you want. You can return it back and whatever you want. And a weak pointer is, use case is very limited, just for observing maybe is an object still alive. Then you can use a weak pointer and call the methods for that. So to sum it up, smart pointers are classes around pointers. They work also with primitive data types like integer flows, but also with their own data types. And they automatically destroy the object when they or when no active pointer points to the object anymore, so when they run out of scope. So the cool thing here is you do not need this delete keyword anymore because it will be destroyed automatically. That was it from my side. Thank you very much and have a nice evening.